All right, welcome back to another fun day. So this will be the start of actual operating systems when things start to get difficult. So I guess no one likes using the Discord either. I posted a little brain teaser in there from last lecture. If exec.ve is the only way to start an application, then if I type ls, who actually is calling exec.ve on ls? No guesses after like 2 days? Or 1 day? Oh, okay, we have some new section, okay. Well, I guess we will find out and kind of dispel some mysteries, but yeah, I guess everyone's time's kind of sucked up by the labs instead of actually having fun and learning stuff on the Discord. So let's get started. So if exec.ve is the only way to, start executing a new program, and it doesn't correspond with creating a new process, which keeps track of the execution of a process, that seems kind of weird. You could just, start a new process that executes a new program. And if you are a kernel developer, you are allowed to make that interface. In fact, that's exactly what Windows does. So Windows has a system call called create process, and that's exactly what they do. But in Unix, it decomposes it into two more flexible abstractions, one being exec.ve that we saw last time, and the second being the fun one we will encounter today. So the other option is instead of creating a new process and then loading a new program and starting to execute it, well, instead of creating a new process, we could just clone the already running one. So you can pause the currently running process, make a complete clone of it, so copy its PCB into a new one, so that's exactly where it's executing. It's all the files it has open, and it's all of its memory and everything like that. And then you now have two copies of the same program executing, and then you'd have to distinguish between them somehow, otherwise you would just have exact clones. And Unix does this through like a parent-child relationship. So whatever one created, did the copy call will be the parent, and it will get, the process ID of the newly created process, and then the other one would get it'd be set to 0, which we'll see, and that's your new process, and that's how you can differentiate one process from the other. And we will see that in code examples towards the end, but believe me when I say it clones literally everything. So there's a strict parent-child relationship between all the processes on your Unix machine, so you could go ahead and go through top and follow the relationships, or I put in the next slide, you could use something called htop that will let you look at the process tree and see what is the parent of what. And then you'll see something special at the top. There's always something called init, which is given a special process 1, which is the only thing your operating system executes when it starts, and it's responsible for doing the rest of the stuff. So you can see here kind of the parent-child relationship. If I run htop, which is one of the monitoring kind of command line tools, its parent is ZSH or bash for you, so it would be your shell. So that would have had to copy itself and then become htop. And we know how a process becomes another one. So the answer to that was, what calls exec.ve? Bash, or your shell, whatever it is. So Firefox would have something similar. So the way Firefox is architected is each tab runs in a new process because, all the processes, as we learned before, are isolated. So if something happens in one, it doesn't affect the other, which is a good thing, especially if you write very unstable software. So this is how you see your process tree. You can use htop, and if you use that, you can press F5 to switch between the views. We can see that quickly. So in our terminal here, I can execute htop, and then over here, I can see all of the commands. So it starts with sbin init and then shows all of the children of it. On your actual machine, there's going to be a lot of different processes. So this is just some of them. it gives you some, then it gives you some accounting information up here. Like right now, I have 91 of them running. So because this machine only has a certain number of cores, which is, I forget how many it has, like 8 or something, 12. It can't be running all of those in parallel, so it has to run some of those concurrently. But again, it's the operating system that decides what gets to run and where, when. So remember we had the kind of process lifecycle before that had, the waiting state created. So it was waiting or ready and then running and then this block state. Well, unfortunately for you, Linux terminology is slightly different. It's kind of a pain. The R state combines both running and waiting, or ready if you want to call it that. So if anything can run, even if it's not actually running, Linux just says, hey, it's running. And then there are 2 block states. There's interruptible sleep, which is the program just saying, hey, I'm going to put myself to sleep because I know I don't have to do any work right now, which is the case for a lot of programs. Like, for instance, running a video or watching a video, you only have to render a frame every 60th of a second, and your CPU is very, very fast. So it would just render the frame and be like, oh, okay, I have almost a full 60th of a second left. I can put myself to sleep for that long, and then I'll draw the next frame when it's time. And then there's 2 other weird states here, the stop state. So the stop state's kind of a weird thing. You can start and stop processes by yourself if you want to, so you can behave as your own manual scheduling. I've never seen anyone use that. It's kind of just for your information. And the last one is a weird one. It is a zombie process, which sounds really weird. Trust me, next lecture we're going to get into even weirder terms than that, and it's going to sound like we're trying to kill people. Yeah.
What's the difference between the interruptible and non-interruptible?
Yeah, so interruptible means it can go to that running state, so it could wake up, but it's probably just waiting to time out. And uninterruptible is it's waiting for like some file I/O, something it can't be woken up from. Like even if you wanted to, you couldn't run it. Yep. Yep.
Can you give an example of uninterruptible sleep?
Uninterruptible sleep is if you're like reading a file or something like that, and you have to wait until you read all the bytes until you can continue. So even though your process is waiting for the kernel to do something, access some hardware, do something, and it needs to wait for that to be done before your program can start running again.
How is it different than the interruptible sleep? The example you gave of the frames.
So interruptible sleep, it could wake you up early if it wanted to, right? So you're not actually hard blocked on anything. You're not waiting for any hardware things to happen. You just decided to put yourself to sleep. So uninterruptible sleep, like if you wanted to, you could, okay, really distinction, you can kill anything in the S state, you can't kill anything in a D state. And kill means you force the process to end, which kill is one of our fun terms we'll see next lecture, but we'll see that later. Yeah?
So stop state is like a state right before either going to S or D, right?
So stop state is just like you moving it to block yourself. So you just say, you can't run anymore. It's in just a special queue where it's just waiting, and then you have to remove it from it manually.
So it's different from the D state in the sense that you have to manage it once it goes into stop.
Yeah, it's like kind of users kind of managing the processes, but I've literally never seen anyone use it. Yeah.
What is the difference between interruptible sleep and runnable? Aren't they both asleep and they both can start running?
So runnable is it's also like wants to run.
Okay.
Sleep is like, yeah, I don't want to run. Even if you wake me up right now, I don't want to run. Yeah.
So like essentially if you push something to the T state, you have to take out manually.
Sorry?
Like if you make something go into the T state, you have to take it out manually or else it'll
Yes. Yeah. The only way to go to the T state is if you manually do it, and then you have to manually take it out. And you can, in Bash, I forget what the key is to do that. You can, I think it's like, I have no idea what it is. You can look it up though. Yeah, so the way this all happens, just to give us a bit of a feel of it when we get into the actual code examples, is as soon as the kernel boots up and initializes itself, someone has to create a process, right? It can't just materialize out of the air. So your entire boot process, all the kernel does whenever it's done initializing is it creates one process and only one process, and it runs execve on it, essentially, and just runs this hard-coded binary. So it just looks in the path. If it's not there, you're not going to boot. And that is the only thing that happens once it's booted, and then that program is responsible for booting up or for creating every single other process on your machine. So that's, and we'll see other things that init has to do. One of the things is creating every single process. On Linux, it's called something called systemd nowadays, but there's tons of other options for it. You could even write your own init system if you wanted to. It's lots of fun, and we'll see kind of how to do that. And yeah, some operating systems will just create some idle process too that the scheduler can run if there's nothing else available to run. Mostly just for accounting, that's just a weird detail that you don't actually need to know. Okay, and then also to explain why our hello world example works is because there are standard file descriptors for Linux. Has anyone seen these numbers before? Okay, so no one's seen the numbers, but people know like standard in, standard out. Yes, hands up. Okay, so on Unix, standard in, standard out, standard error are hard-coded numbers, and they're file descriptors. A file descriptor is just a number. So this is just by convention. It only works because everyone on the planet has agreed to do this. So the number everyone has agreed to is 0 is standard in, 1 is standard out, and 2 is standard error. So that's why when our write system call, we wrote to file descriptor 1, and we wrote hello world, and it appeared on our terminal because that's exactly standard out, right? So you can tell that a terminal emulator's job has to, translate key presses from actual keyboard inputs and then converts them to ASCII and then puts them on that file descriptor. And then anything that gets written out to them, which are just ASCII bytes, have to get converted to the actual pixels on your display. And that's the job of the terminal emulator. And the fun thing about this too is everyone's like opened a file before and had to write somewhere, right? So the fun thing about Unix and why it's this way is you can have any program you want that uses these file descriptors write to a file without you having to ever open a file or do any file handler code. So what you can do in Unix is you open a file, it just gets a file descriptor. So you could open a file as file descriptor 1 and then run that program, and then it will output to that file instead of going to your terminal, and you never have to write any file, or you never have to open the file or do anything. So it's actually kind of great, and you will get some practice doing that later. But we need to get through today's lecture. But if you want to check open file descriptors, and this is how we're going to check, kind of do some sanity checks. Yeah.
Sorry, so there was an input and output, which would be from a file or out of file. And then what is, the last one was error?
Yeah.
What is that doing?
So it's just another place to write bytes to. So.
But if it's not writing it to that specific file, where is error stored?
Well, you don't know what one is at, or what file descriptor 1, 2, or anything is connected to. By default, they're all connected to your terminal, but you could change them to files if you want.
Oh, so file descriptor doesn't mean that it's connected. It's like a part of a file that you're writing to, right?
No, you're just writing to a number, and then that file descriptor can represent literally anything.
Okay.
And we'll see how to play around with that later in the course. Yep.
So the std in can be used to like write as well as read from a file, like if it's connected to a file.
So it doesn't have to be connected to a file. So your terminal emulator will connect it. So you can connect it to a file if you want, and that's through doing some terminal stuff that we'll see later. But it just gives you the flexibility. All it is it says that, hey, you can only read from file descriptor 0, and then you can write to file descriptor 1 or 2, and that's how standard terminal applications work. So if you print out, like, there's like printf, and then there's fprintf that has standard error, it just goes to 2. Yeah.
Can you actually open these files, like, see them?
Yeah. So here, let's. Here, I'll even execute hello world. So I guess we haven't super seen fun terminal stuff yet. Oh God. Okay, so even if we go back all the way, let's go back to lecture 1, right? So we know our hello world, oh, whoops. There. All right, so we know our hello world, it just prints hello world, right? And that just is a write to file descriptor 0. So if we haven't, one of the things you can do is bash. It's called a redirect. So you just put like a little arrow, and then you could say I don't know, output.txt. So what that'll do is the shell's nice enough for you that it has file handling code. Your shell will go ahead, open a file called output.txt, and then connect that to file descriptor 1. So that when your program executes, which just writes to file descriptor 1, it goes to that file. So now when we do that, we don't see any output here. And we can look, and yeah, there's no output. And if we look at the file, it says hello world. So that's where our output went. Yep.
Afterwards, does it just like remap file descriptor 1 back to the terminal afterwards?
Well, so after that application dies, right?
It automatically goes back to the terminal?
Yeah, so we'll see why. It will make more sense once we see how to create processes. Yeah.
So what we use as a terminal is actually a terminal emulator? Like,
So there's a terminal emulator and a shell. So terminal emulator is going to, handle all your keyboard input and stuff.
so like this is what we're seeing right now, is it?
Yeah, so this part is a terminal emulator that you see, but what I'm typing in is the shell.
Is the shell, okay.
Yeah, so you can write a shell. Shells aren't actually that hard to write, but terminal emulators are a pain. Yeah,
When you did the C with the cat output.txt command,
sorry?
the second command, when you did the second command, the cat one.
Yeah.
So did like the file get connected to std, like the file descriptor 0?
Oh, so cat just reads that file and then, yeah, so cat will read that file and then output the results of that file to file descriptor 1, and it's default again, so it just goes to the terminal. But if you want, I guess you could do, hey, let's do it again, right? Cat that file, so then cat will read that file, output its contents to file descriptor 1. Now we're going to have our shell throw it to o2.txt, so it doesn't give any output, and we see it again, which is kind of weird, but like if you're catting to an output, it's kind of weird, but yeah.
So when you're writing hello world, that would be writing it to one, 'cause that's,
Yeah, it just writes to 1. You don't care what it is.
and then if you're reading from something, that's reading from 0. 'cause
Yeah.
it's the input.
Yeah. Yeah, so if you write a C application and then you interact with it, go ahead and strace it. You'll see a bunch of read calls from 0. So you can always, in this course, you can always have fun stracing things, and then we should be able to explain it in class behind first.
Can you see where the file 0, 1, and 2 lives, or is it just like it's not actually on the system, then you can see it?
Yeah, I'll show that in just a second. Yeah.
So can there be more than 2 processes with the same file descriptor at the same time, or the same one?
Yep.
So that would just write to both files at the same time?
Yeah, so that's what's happening in our shell. It's all being outputted by the terminal emulator, and you're actually sharing stuff. It'll make sense in a little bit. What was I going to do? Oh, yeah, list of open file descriptors. So there's, let's see, this slide. So you can actually see what file descriptors are to answer your questions. Is this proc file system that it's all folders, and the folders are by process IDs, which are just a number. And then inside of it, there's an FD directory that has everything named 0, 1, 2, and whatever else it has open, and you can see. So if we look at our terminal emulator, which is going to have a lot of stuff, here, I'll make this bigger. So there is a special symlink called self that will get the process ID of the self. And we can go ahead and see all the file descriptors it has open and what they point to. So this has like 50-something file descriptors open. But if we want to scroll all the way to the beginning, we can see 0, 1, and 2. So the standard ones all point to this weird thing called device PTS1. So that's something that we probably won't learn. That's a terminal emulator that runs and is supported by the kernel. It's called a pseudo terminal. It's like some weird hand wavy thing, but that's what's represented as. So that's exactly where all your bytes are going to. Yep.
So like when it reads 0 arrow the file descriptor, you're reading from that file descriptor?
Yeah, so these are all like symlinks. So it's just the name of the file. So if I could access, proc self fd-0, and then this is what that is actually pointing to. So there's pointers in files too. Great, eh? So you can see other stuff as open, like file descriptor 103 goes to this downloads. I don't know why it's downloading something. VS Code is doing something. So yeah, you can see what your system's doing. But yeah, it's got some fonts open. You can see all the files it's actually using. Oh yeah, that's because I'm using the weird VS Code one. Okay, so yeah.
I saw like there were different type of file descriptors, like a 103 or so. So are they like related to a specific process, or?
Yeah, so they're related to whatever that process was. So here, right, it'll just list everything open. And I guess in the interest of time, you can do ls of and then put a file name, and it'll do the reverse lookup. So you can see any processes that have a certain file open, especially if you want to know, hey, I have a secret file, or what's writing to this file. So you can even do it, right? The standard C library is just a file like anything else. So you can actually see everything that uses the standard C library if you do ls of, libc, and you'll pretty much get back every single process on your machine because everything uses C, even at some point. Okay, so now we're going to get into the fun stuff. So on POSIX systems, right, you can find documentation using man, which is usually your friend. We saw execve last lecture. Today we'll see a system call called fork. And then we'll see wait in the next lecture. And then usually you just do man and the function name to look up documentation for it. But unfortunately for fork, if we do man fork, we get this like weird awk extension modules thing that doesn't help us whatsoever. Unless you're writing awk, I guess, which thankfully you don't have to. So if you want the real documentation, the number 2 is for system calls. So if you do man2 fork, you'll get the Linux programmer's manual, which actually gives you, where the header file is and what the signature is. So fork, doesn't take any arguments and returns a process ID type, which we'll see shortly is just a number. Okay, so here is the fork API. So it takes no arguments and it just returns something. So it can only return 3 things. It returns -1 and then sets error no, because it's a C function, if something bad has happened. And this is the only way to create new processes. So if this fails, your computer is probably dying. So you probably don't need to check for errors that often, but you can if you want. And then usually if it is actually successful and creates a new process, we now have 2 things running, and the only way to differentiate them is the return value of this. So in the child process or the newly created process, the process ID will be equal to 0, exactly 0. And then in the parent, whoever created that new process, it will be some value greater than 0, and the number it gets back will be the process ID of the child process, so it can actually keep track of it. So this is where things get fun, because so far, our execution has started at main and went until exit happened somehow. That's no longer true. Yeah.
Is it just any number greater than 0?
Yeah.
Doesn't matter, like if it's like a 10 or like 50. Does it give different information about it?
No, so it's just a number to identify the process.
Just a random number, arbitrary number.
Yeah, they just have to all be unique, so you can uniquely identify a process. Yeah.
How does it like return two things at once? It returns 0 for the child process and greater than 0 in the parent process. Like, does it store it somewhere?
So it's an exact after the fork, it copies the process completely, and now there's two things running, and the only difference is that value. So this one's running with PID, or the PID equal to 0. This one is PID greater than 0, and now there's two things running.
This is the process ID.
Yeah. Yeah.
What does it mean to be having a newly created child process in the parent process, right, which is greater than 0 case?
Yeah, we'll see it in a second. I'll show a code example. Yeah.
Can you just state again, like, what exactly is like -1, 0? Like, what does that represent?
So fork, it just returns a number, right? So if you read the documentation, it says there's only essentially 3 options. If that number it returns is a -1, it's an error. If it's a 0, it means this is the newly created process, which we'll see in a second. And if it's greater than 0, it means it was the original process. So we'll see it in a second. Yep.
So when you use fork in the terminal, which specific process is it telling you about?
Let's use the system call instead. Okay. Yeah.
Like, does fork essentially create a copy of the parent process?
Yep. Yeah. So let's here. Wait 1 second. Let's just run the example and see what happens, because code doesn't lie to us, right? And code's perfect. All right. So before the fork happens, our world is how you've learned it. Execution starts at main, although we know that's not really true because it has to load the C standard library, blah, blah, blah. But let's assume that execution starts at main. So here we are at main. The first thing we do is call fork. So right before it, there's just one process running main. First thing it does is call fork. Boom. Now there's 2 copies of the exact same program, and they are both executing at this point, right? Now, so there's 2 things executing here. And one will be, PID greater than 0. The other will be process ID equal to 0, assuming that my computer is not dying, which hopefully it's not. So at this point, there's 2 things to run. The kernel gets to decide what to run, and you hope it runs things in parallel to make things as fast as possible. But this is why we have an operating system, because you don't have to make the decision of who gets to run next. So there's going to be 2 processes. We don't know who's going to execute when and where, but for any one process, it will follow normal execution. So if we consider the first one, the original one, the process ID will be greater than 0. So this if statement will be true, right? And then it will print off parent return PID. So it will just print off the return value it got from the fork call. And then it will print off its own process ID through this system call, get PID. And then it will also print out its parent's parent ID. So whatever created it, which is the extra P here. So parent process ID. And then we just sleep here for a little bit. You'll know why I do this in the next lecture. And then, right, so it would be in that if block, and then it would go ahead, fall out of it. It wouldn't go into else if or else because it went to the first if. And then it would return 0, and then that process dies, right? It returns 0, it's dead. So that's what would happen in the original one. And then the other case is when process ID equals 0 for the newly created child. So in the child, remember at the point of the fork, it was exactly the same, and the only thing that's different is the process ID. So it would continue to execute. Now this if statement is not true because process ID is equal to 0. So it would go into else if, and then this one's true because it's equal to 0. Then the second process would print child return process ID, whatever it got from fork, which if this isn't 0, then nothing makes sense anymore. And then it prints its process ID, which should probably be related to what the parent got. And then the child's parent ID, which should be whatever created it. So let's go ahead and execute that, and then we can take some questions. So, fork example. All right, so here we go. And the order of this is actually not deterministic. We just kind of got lucky. So in the parent, right, so the parent returned or child returned is what they got back from fork. So the parent printed first, it got back 3,554, which that is the process ID of the child. And thankfully, if we looked at the child's process ID, it matches, right? So that makes sense. And then the parent's process ID itself is 3,553, which, you know, that's itself, which corresponds to this, right? That's the child's parent ID. It's what created it. And then, so that makes sense. And then we get to see whoever created the original process, which is 1,449. And if we want to figure out what that is, well, there's that fun proc file system, right? We can go ahead and look it up. So if we look up process, 1,449, we can actually see in state or status, there's something called name. So we can see who created it. So the shell created the original process, and then that process created another process. Yeah.
So the return PID is what it's.
The,
Like I'm confused what the three different values represent.
so the return PID is the return value of the fork call.
Okay. So the fork created a number called your number 3554.
So the fork created two processes, and one has the process ID of the newly created one, and one is the newly created one. So it has two, it's, okay. So at the time of the fork, it completely copies the running process. Complete copy, exactly the same. The only difference is going to be the return value of fork. So now there's two things executing. One will have the process ID of the newly created process, whatever just got created from the fork. And the other will have a process ID of 0, and that means it's a newly created process.
So originally that process had a process ID of 0.
No. So the original process ID was the running process, which was the parent. So this is the original running thing, right? Because its parent ID is this, which is the shell. So I executed this, and then the shell ran it. So
This process has 3553.
yeah, so the original process is 3553, and it created 3554.
So the child's ID is 3554.
Yes.
So where does 0?
So 0 is the return value in the child itself.
Oh, so each process has two values. It has its own value and then its return value?
Yeah, so at the point of the fork, right here, there's two processes running, right? And the only difference is the value of PID.
Right.
Otherwise, they're exactly the same. And they're two processes, they're running. Well, they could be running. They're going to run. Yeah.
Can you explain the code that you ran at the end, the CAD?
Oh, so this was, I just looked up this process ID to figure out what its name was. So in proc, right, you can look up stuff by PID. There's a status file that'll tell you all sorts of stuff about the process. One of the things is the name, so I just print out the name. Yeah.
So fork returns both the values at the same time, or does it return one at a time?
Okay, so fork just returns one value, but now there's two processes.
Okay, but which one? Because it's supposed to return either 0, like 0 for the child and the process ID of the owner.
No, so there's two. There's two. So there's our running process, which is, 355.3, right? This is executing. It hits the fork call. Fork. And then it creates a new process called this. And they're both executing at the next line, but in this process, PID equals 3554, and this one, PID, whenever it continues execution. So now there's two things executing at this point, right after the fork. One's going to execute with PID equal to this, which was the original process. One's going to execute with PID equal to 0, which is the new one. Yeah.
Why doesn't it just continue with the like 3553?
What?
Why does it? So I created another process.
Yeah, you created this.
I created this. So why is my PIDs changing to the one that I created?
It's just the return value from fork. You're not changing your own PID.
It's just the return value.
Yeah, it's just the return value.
Oh, okay.
Yeah, yeah.
So now that, oh, sorry, me?
Oh, yeah, go.
Okay, so now that there are two processes, like parallelly, there are two processes that are created.
Yeah.
So both of them will run the code for both of the conditions, which is PID greater than 0. And
No,
PID less.
no. So at this point, all right, this is important. Right after the fork, there are now two exact clones of each other, right? There are two exact clones. One, so you have to think about two different executions. So in one, process ID is this one, right? So this one will execute until main, and then this one will execute until it exits from main. So there's going to be two. It's not, the same value. There's now two copies of the exact same thing, and the only difference is the value of this variable. Here, back first. Yeah, so after the fork, right, there's now two running processes, the original one and the new one. And the way I can identify what the new one is the value of PID is 0.
But it also has another value, which is 3,554. What does that represent?
No, so I'm only printing off one PID here. So it's only this returned. Here, I'll execute again. So only this returned represents the value of that got, only this returned is the value from fork. So the other ones are just, I did system calls, right? There's get process ID system call and then the parent's process ID system call. So there's three numbers. For both of them, they're all in the same order. It's what was returned from fork, what's my process ID, and then what's my parent's process ID.
So my process ID is different from PID, or is
No, process ID and PID mean the same thing.
but the return value from the fork is the PID too?
So it's just a number. So the return value from fork in the original process that created one is going to, its process ID is going to be equal to the process ID of the newly created process. So the return value in this, if we call this the original process, the return value will be equal to the child. And then in the child, by definition, right, its process ID returned from fork is going to be 0, right? So here. So yeah, so PID, don't get confused with the term process ID. Process ID is just a number. Every process has its own unique number. Yeah.
When you call the fork, like the fork command in the code,
Yeah.
so when the second program is created, the child program,
Yeah.
does it start like from the start of the program, like calling the libraries and everything, or
No.
is it like
No, exact copy from when the fork happens. So, okay, holy crap. All right, yeah.
Wait, just to clarify, like 3553 and 3554, they're the names of the process.
So that's the process ID. So a process ID is just a number to identify it. Every process has a unique ID.
Okay, and then it just happens to change after we apply for it.
Yeah, so I called it again. So the numbers I used here were used before, so it just generates new unique numbers.
Okay, so now 3553 of the parent has become 3554.
So this one, 3553, is the parent, and then 3554 is the newly created one, which is the child.
Okay, but what I'm saying is like, there's like names of the process, which in this case are like 3000s, right? And then the IDs that you get from it?
So the 3000s and stuff, that's the process ID. It's just a number. There's no difference between, like, the name could be the name of the command you had, but process ID is just a number that identifies uniquely what the process is.
Okay, but it just changes for both after you apply fork, right?
No, they stay the same, right? And then in one, I have
two questions. One, if the process ID is the 3554, why did you write process ID is equal to 0 underneath it?
Okay, sorry. So this is the running process, right? This is the actual executing process.
The child, right?
Yeah. So this is the running, whoops. So there's only, before fork, there's only this, and it is executing. It has process ID 3553. The process ID will never change. This is one process, and then it calls fork, and then the return value of fork is 3554,
Okay.
and this is a newly created process.
Okay.
And at the time of the fork, they're exact clones of each other. And then the return value it sees from fork is 0.
So then because it's a clone, it also runs fork.
No, so it's right after the fork. So here, let's see. Let's do something more fun because we're running out of time. All right, so here, before questions, I will create a variable. This variable is called x equals 1, right? So at the time, if what I'm saying is true and everything is an exact copy, and here, I'll even do a print statement, printf. Okay, so here's, I set x, right? Up to this point of the fork, we all know what's going to happen, right? It's going to declare an x, set it to 1, do a print, and then some magic will happen after fork. But before fork, we're all good, right? So if I execute this just by itself, it's unused. If I execute this by itself, how many times am I going to see I set x printed out? Once, right? Because it's before the fork, we're still in our normal world. So if I print f after this, right? So how many times will that get printed? 2, right? One for each process. Now, let's do the fun part. Parent. Okay. Now if I do that, right, we should see after the fork printed twice, so because there's 2 different executions. One will go in the parent branch, one will go in the child branch, and they'll both print off x equals to 1, right? Hopefully. Okay, so they both print off x equals to 1. Yeah. Yeah, so you'd call exit or return from main. That's the only way to exit a process.
In the child, like, if statement, you just return and it's after all those things you have more stuff, then the child won't just stop and then keep going.
Yeah, so like here, right, in the child, the first thing I could do is be like, this is too confusing. I'll just exit immediately. And then in that case, that process will die immediately, right? And nothing else will get printed, just the parent stuff. Yeah.
Is a process ID always an integer?
Is a process ID what?
Always an integer.
Yeah. Yeah, process IDs are just integers.
Is there any difference between the type of the process ID and an int? Like if you get int the ID is equal to fork?
Yeah, if you want. Okay. All right, let's settle down 2 seconds because it's going to get even worse. All right, so we're about to get worse. So here, I'll say x equals 2. Now what happens? So in the parent, I will set x equals to 2. So In the parent, hopefully x equals 2. What does someone think this will print? 1, right? Because it's an exact copy at the fork, but then one of our principles is that each process should be isolated from each other. So if I go ahead and run this, which is fun, I'll see that in the parent, x equals 2, and then in the child, x equals 1. And then you might be saying, oh, what about if it's just, updating that variable first? Well, we'll make sure it writes so we can just put the child to sleep for a second. So we're guaranteed that the parent writes that value that updates x to 1, updates x to 2, and then prints out its value. And then we'll see if it changes. So who thinks in the child that x is now equal to 2? All right, so a process should be complete copies at the time of the fork, and then other than that, they should be isolated from one another. So if the value changes, if you can affect the value of one program from another one, that's bad. So if we do that, we can see that, hey, in the parent, x equals 2, and after, hey, x equals still 1 in the child because it never changed it, right? And to even illustrate this even further, that you might be like, oh, well, what about the address of it, right? What about if it's like pointing to a different address? So let's see what the address is of x in both of them. So if it's an exact copy, like I'm saying, the addresses should even be the same, which should be quite remarkable. And then if I do that, oops, I get rid of the sleep. Whoops. So if I do that, and I look, oh, Jesus. If I do that and look at all the addresses, the address of x in the parent is blah, 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 A24. Hey, in the child, it's blah, 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 A24. They're exactly the same. Yeah.
I'm just trying to understand that. Why would the processes both be coming from the same address?
So they're both the same address, right? But they're not changing the same variable because we just tested that. So these are obviously not physical memory addresses then. These are all virtual memory addresses. So when a fork happens, I said exact copy, and that's down to the pointers, down to what they actually point to. So the operating system, right, the kernel has to magically fool you about this because they look exactly the same, but clearly they can't be pointing to the same physical address because that makes no sense, right? So the kernel, which is what you have to do in this course, you have to make this illusion true. So they're both mapped to different addresses, but because they're virtual addresses, they look exactly the same.
So does that mean that they're virtually pointing to they can't be pointing to the virtually same place of where the x variable is, right?
No, so because they're virtual addresses, they're like a layer of indirection. They can point to whatever memory. So in one process, that address points to some block of memory, and then the other process, that same address gets mapped to a different block of memory.
Okay, so essentially, like, even though we called x same time 3 times, they're all in different places of memory, and the processes figure out where it's like.
So within a process, it'll stay in the same spot after the operating system decides where it is. So there's only 2 x's here.
Oh, not the one at the very beginning?
So the one at the very beginning gets copied. So then after it's copied, there's 2 of them. Yeah. All right. Any other questions about this? Because we have 1 minute and it's going to get way worse. So I don't even have enough time to go through this. So here's another one that in main, all it does is execute a loop 4 times, calls this function called createProcess with a number, and then it immediately forks. So right, so far there's only one program running, so it immediately forks, and then process ID is greater than 0. It's the original process. So thankfully for you guys, it just returns. And then the new child process goes ahead here, prints off what process it is. Whoops. Prints out what process it is, and then thankfully calls exit so nothing weird happens. And if I execute that, I should see, all the different processes printing out all sorts of different values. I guess I'll have office hours after this, but 2, if I really want to break your brains, if that's not bad enough, which I guess we'll carry into the next lecture. Anyone want to hazard a guess if what would happen if I did, well, 1? So let's see what happens when I do that, which is a great way to end the lecture because I'm about to brick my computer. So nothing will print out. My thing just went blank. It's now unresponsive. And what that does is, hey, as soon as it executes, it will call fork. We don't even check the return value because we don't care anymore. It creates a process, and then both of those, right, exact copy, then both of those would go back up to the loop, and then they both fork. Yeah, so now they both fork. So now those 2 processes each create another process. So then you have 2, then you have 4, then you have 8, then you have 16. And you can do that to your friends. Tell them to write that and execute it.
Realize it's messing up and say, no, stop.
No. So it's here. Yeah, see, resource temporarily unavailable. Fork failed because I ran out of space. All right, so we'll continue these examples later. I guess I have office hours soon-ish too at like 4. All right.